My name is Melissa Ferry. For this video for Lab 4, I will talk about oscillations involving a spring and all the forces and energies involved in this movement. So in this video, the main concept we'll talk about is energy. As you know, there are many different types of energy, including kinetic energy, potential energy, thermal, chemical, and electrical. However, today, we'll only focus on potential and kinetic. In addition, in this video, we will focus on the law of conservation of energy, which states how the total energy of a system cannot change. Since the system includes the spring, the small mass in the earth, and nothing is notable in the surroundings, which is outside this box, the total energy must not change because there is no work. Also, we will use forces from objects, such as the spring of the earth, to find new positions and compare the predicted position data with that of the model. And we can see how the predicted and the model are basically the same. In addition, another result we'll find is that the potential for the spring and the potential for the mass, they work in opposite directions, and along with the sum of kinetic energy with it, the energy is zero. So conceptually, we know that the change in energy is equal to work. We can also write this by the final energy equals the initial energy plus work. Work is zero because there is nothing in the surroundings that is acting on the objects. Therefore, delta E has to equal zero. In addition, we have to focus on potential energies. For the spring, it's 1/2 kx squared. And for this, we need to know the spring constant K and the distance between the relaxed spring, which is L sub O, and the stretched or compressed spring. And you can find K by using a formula 4 pi squared times m divided by the period squared equals K. And you can find the relaxed length by doing the magnitude of the length minus mg over K, once you find K. In addition, we have to know the kinetic energy because the block at the end is moving, so it's 1/2 mv squared. And once again, so the energy is equal to, and these are the deltas, so it's going to be the change in this potential energy, the change in this potential energy, plus the change in this kinetic energy has to equal zero. Once again, we have to update the position, and we use Newton's second law, which is the basis for a lot of the past labs. So final velocity equals initial velocity plus F net divided by mass times delta T. And then the old position equals the new position plus the final velocity times delta T. Therefore, we need to find the forces. As we know, the force of gravity acting on the block is in the y direction, and it's mass m times g, 9.8. We also know the force of the spring is the K constant times x. And this picture indicates a stretched and compressed spring. So some main initial conditions is the mass, which is 0.402, the position, which I obtained via tracker. It starts out with zero velocity. We know G, 9.8, spring constant, the relaxed length. Once again, these is how you find the system energies, just translated to Python code. As you can note, the H component here changes position.y because the block is always moving in different directions. In addition, we can focus on the forces, which tells us where the block moves. As you can note, for the force of the spring, S depends on how much the spring is compressed or stretched, as in if it's not compressed or stretched at all, this net force would be zero. So now we can focus on the energy graph obtained via Python. As you can note, red is the change in the potential energy for the spring, green is the change in the potential energy of the block, blue is the kinetic energy, and yellow is going to be the sum. As you can note, the kinetic energy is fairly constant, except in the middle it slows down. You can tell this because the energy does not reach its highest peaks. In addition, you can note how the potential energies and kinetic energies are all at some point zeros. Finally, we can conclude that even though it's oscillating, it basically does the same pattern. As you can note, how the tops of the waves are roughly in the same position each time, which means it does have random motion, but for the most part, it follows a trajectory. Now we can watch the trajectory. The red is going to be the result via tracker, and the blue is the result obtained via Python. As you can note, the model does do a very good job in obtaining the position, but just in general, the tracker one, it spins around because it's oscillating and it's also moving up and down. In addition, there is drag force with the air. Even though it's very tiny, this is what makes it do a less distance compared to the model. So we can conclude that the energy principle is indeed satisfied because there's no work done, delta E must be 0, and as you can tell from the graph, the yellow line is at 0. So throughout the thing, no energy comes in, no energy comes out, everything stays in the system. So as you may expect, there should be the same oscillation periods, however, it is different, and it's how many seconds for one complete cycle. For X, it's 1.66 seconds, for Y, it's 1.52 seconds. That means that it moves more in the X direction than it does in the Y direction, which is why it takes more time for X. So in conclusion, we used the energy equation, which is delta E equals work, however, there's no work, so the change in energy must be 0. And we found this via finding potential and kinetic energies. Thank you.